When?
We are ready to start. So maybe a brief introduction. Let's go to the first session.
Are you a master student?
Yeah, in computer science.
Computer science. What are you interested in?
Machine learning, let's say.
Machine learning. What year?
Second.
Second year. Okay. So let me get this.
I cannot read this.
It is working. Yes, it's real. Can you speak closer?
Yeah.
Let's speak from keys for now and then we'll see.
Okay. Hi, everybody. This is Clement. He's a master student. And today he's going to be presenting Lincoln from HPCA 2025. His main interests are machine learning and what else?
High performance computing.
High performance computing.
That's
Okay.
Right.
Sure.
So hi everyone. Today I will be presenting Lincoln, which is real-time 50 to 100 billion parameters LLM inference on consumer devices with LPDDR-Interfaced compute-enabled flash memory. So first, an executive summary. I will read it with you. So large language models cannot fit into the limited DRAM of consumer devices. Flash storage features high capacity but cannot provide adequate bandwidth to perform LLM inference due to the lower bandwidth on NAND flash and the lower bandwidth of the interface. The goal is to enable real-time inference on consumer hardware. The key ideas of Lincoln is utilize hybrid bonding to fuse flash with LPDDR and exploit the memory interface. It employs a custom storage design based on SLC NAND, flash with shorter bit lines and more planes to increase parallelism. It uses also in-storage processing on the logic die to process fully connected layers to alleviate data movement overheads. And for the evaluation, it removes the bottleneck between flash and NPU, and the NPU can use the flash as efficiently as with DRAM. It also achieves real-time token generation. It achieves 11 times and 47 times sped up in prefill and generation phase against the base with speculative inference. And it also achieves 3.6 times lower energy consumption per token against base S for a cost of around $191. It is hence superficially competitive against other types of LLMs. All right, so this is our plan for today. First, why do we want to run LLMs on consumer devices? There are 2 points. First is privacy issues. LLMs can connect a lot of private data. We can recall last year during the summer, Microsoft tried to release Microsoft Recall, and who was sending like local screenshot to the cloud, and this had a big backlash. And the second thing is server inference is very costly. So reportedly, OpenAI is losing money on $200 subscriptions. So companies want to push LLM costs to the consumer. All right, some backgrounds. What are the main points? So first, we will talk about LLMs. We will today only talk about decoder architecture. They have 2 main components. First are fully connected layers. They only apply token-wise, meaning each token only computes with itself, and this is where most of the parameters in the large language model are located. Then the second important things is self-attention. We use key and values of previous tokens, so it's not really important to know exactly how it works, but what is important to know is like we can use only key and values from previous token and to compute current self-attention. And since this enables, since we only care about previous keys and values, this enables caching, and we only have we don't have to run self-attention on the whole sequence again. All right, so because we have caching, we can split the execution of LLMs in two parts. First is prefill, where the LLM is computing the prompt. So here, for example, it will compute I think apple in parallel, and it will output one more token. So here there is. Then there is a decode phase, which takes every time the prompt plus the generated tokens and generate one more token every time. For the prefill phase, we compute the whole thing in parallel. So this is mostly general matrix multiplications, and it is mostly compute bound. For decode, since we have to go through all the layers, this is mostly memory bound, and we are using mostly general matrix vector multiplication for this part. Okay, one little thing on speculative decoding. The idea of speculative decoding is using a smaller draft model that can generate multiple tokens really fast, and then we go through one pass of the bigger model to and it can verify all the generated tokens in parallel, a bit like the prefill phase. Also, we are running every time bigger and bigger models, and usually they are better and better. So we can see here with A100, which is really fast. It is still not enough to be able to run LLM inference for 100 byte models. There are two problems. First is the capacity. It has only 40 gigabytes of memory, and the second one is bandwidth. Even if we had enough capacity, the bandwidth would still not be high enough to calculate in real time the inference. Yeah. Then the memory systems we care about today, we will speak about DRAMs, which has high bandwidth to the neural processing units, NPU, around 100 gigabytes per second. But it has usually low capacity in mobile devices, around 16 to 64 gigabytes. Flash has higher memory capacity, maybe in the terabyte range, but it features low bandwidth, around 10 gigabytes to the NPU. Also, mobile devices use low power DDR, which is a version of DDR that uses less power and has higher bandwidth. The last thing is about hybrid bonding. So the idea of hybrid bonding is placing the logic and the memory side of the flash on separate wafers. This enables better optimization of both die, so we have better logic and higher array density, and then we just stick them together. So yeah, here you can see how it works. Instead of having the logic under the array, we have the logic on a separate wafer. And this has lower cost than previous method, like through silicon bias. So what do we care about? What is our goal for this LLM? So first, we want low latency token generation. We have a target of 4 seconds for prefill and 0.2 seconds for generation. Then we want to be able to run big LLMs. This is because bigger LLMs are better, as I said before. So we want to run the biggest LLMs possible. And also we would like to have affordable costs. and low energy consumption. If we double the cost of the device or half the battery life, then it will cause some problems. Okay, so for up to the motivation, weight loading is responsible for 94% and 92% of latency for prefill and generation phase. Why is that the case? There is two reasons. First, large LLMs are too big for the RAM, which has high bandwidth. So if we have a large language model with 100 billion parameters quantized to 16 bits, this is 200 gigabytes. And since it cannot fit into the RAM, it has to reside most of the time in the flash. But the flash has low bandwidth to the NPU. Yeah. Also, the flash has another problem, is even if we consider only the read latencies, meaning we consider we have infinite I/O, it will still not be fast enough to attain real-time token generation. This is because the read latency of the SSDs are too low. So we will, Lincoln in this paper uses SLC NAND flash, which has the highest internal bandwidth. It is also the most expensive, but it's a good trade-off. We also care about, so there is only 1 bit per cell, and it has also the highest program erase cycles. The reason why we care about program erase cycles is when running an inference, we will read through the model many times. We will go through the model every time and many times. So we want to be able to have high read P cycles. Yeah. All right. So what is exactly Lincoln? There are three key ideas. First is using a modified SLC NAND flash to increase internal bandwidth and P cycles. Then using the existing high bandwidth LPDDR interface to provide high flash bandwidth to the NPU. And the last thing I haven't yet talked about is utilize in-storage processing for fully connected layers in the decode stage. So let's go through them one by one. First, what do the flash die look like? So there is one layer of flash, which is an array, and one layer of logic behind. And we hybrid bond them together, as I explained before. Yeah, so they also shrink the size of the plane to increase the shorter and use this shorter bit length to increase the internal bandwidth. One die can achieve 34 gigabytes per second. Also, on the logic side, we have the FP dot product, and this enables to calculate general matrix vector multiplication directly on the logic layer. The last thing is they also add the little ECC unit, and the reason is because sometimes SSD can be modified if you read them too much, so you need to have some error correcting codes. The evaluation showed that using external ECC in the global buffer somewhere would counteract all the speed gains of using the floating point dot product. So they put also a little ECC unit directly on the logic side. Okay, the package, we just stack to the different dice together with the DRAM layers, and then we use cheap wire bonding to connect them to the substrate. Here you can see DRAM and flash dice are sharing some channels. Also, one thing in the evaluation, there is two packages mentioned. There is Lincoln 2 and Lincoln 4. So one has 8 dice and one has 16 dice. This is just, so yeah. Let's go through the inference. In the prefill phase, as I said, it's mostly general matrix multiplication. So we cannot use the FP dot product to calculate the matrix multiplications. So the NPU does everything. It loads the weights from the flash into the NPU. Then it calculates self-attention project, yeah, and then it calculates also the different fully connected layers. In between, here in the generation phase, it also stores the key and the values in the DRAM. In the generation or decode phase, the NPU calculates only the self-attention. So we can see here the queries, the keys and the values are generated in the flash. Then it sends these three matrices into the self-attention, which calculates the self-attention using the keys and the values loaded from the DRAM. Then it sends them back to the Lincoln in a flash compute, which project and calculates both of the fully connected layers. This reduces data movement because all of the weights of the fully connected layers, which have the most parameters in the model, are computed directly near the flash. Okay, so for evaluation, we don't care about a lot of this, but they are using 3D-FPIN for latency estimation. They are using also other simulators for heat dissipation and SSDs, but yeah, we will only talk about 3D-FPIN. And also there is a conservative 32 tera operation per second. Today, most of the laptops that are shipped have more than 32 tera operation per second, even in lower end laptops. So here again, there is this Lincoln 2 and Lincoln 4 package. I will mostly be talking about Lincoln 2 because this is the one they mostly talked about. So this is, yeah. If we remember, as I said before, our goals were low latency token generation. So 4 seconds for prefill and 0.2 seconds per token in generation phase. We wanted to be able to run big LLMs. And the last one was affordable cost and low energy consumption. So without further ado, they achieved real-time token generation using big LLMs. As you can see here, there is between 1.6 and 3.7 seconds of latency for prefill phase, and between 0.08 seconds and 0.2 seconds per token for generation phase. So except the very big model, it solves real-time token generation. I would like to point out, those are already big models. Usually you would already be running maybe until 8 billion parameter models on your machine. Against not using Flash, we can see that there is an 11 times sped up for prefill phase over a base with speculative decoding. And during the generation phase, there is a 47% speed up for decode phase over base phase. As you can see here, the weight loading latency is totally removed. So the LLM inference becomes again memory bound, compute bound, sorry. And it is not memory bound anymore. For the energy, there is not a lot of difference for the prefill phase. There is only maybe 30% of difference between using Lincoln Flash or no Lincoln. This is because the weights have to be loaded in the NPU anyway. But for the generation phase, there is 3.6 times less energy per token in generation phase. Yeah. Also, they considered heat, which could be a problem, and even considering 300% AOR in energy consumption, they only get around 6.6 Kelvin increase on the LPDDR, so this is acceptable. All right, the last one was cost, and as I said, it cost about 191 to 382 for 2 package Lincoln. This is using existing technologies, so this is kind of a hard cap on the price of the technology. And in the papers, they also compare this to ChatGPT, which costs $20 per month, and so they conclude, okay, so this is sufficient. Okay, so let's go to the conclusion. Let's recap what we have seen today. So Lincoln uses a modified SLC NAND flash in LPDDR package to solve the two existing memory bottlenecks in LLM inference. So first is the internal reach speed of traditional SSD, which is not high enough. And the second is bandwidth between flash and SoC, which is solved by putting the package directly on the LPDDR. This enables large LLMs to be run on consumer devices, something that was not previously possible. And it speeds up by a factor of 47 times, while token generation while decreasing energy consumption by a factor of 3.6x. Okay, so with that, do you have any questions on this part? All right. So let's go to the strengths and weaknesses of the paper. First, I found it is orthogonal to much of the LLM on the research on LLM inference. This is because usually you would have research on quantization, you would have research on knowledge distillation, but this is kind of something else because it can also benefit from Lincoln. So Lincoln could be running maybe 400 billion parameters models with 4-bit quantization, for example. Yes, then it only uses existing and implemented technologies. So even if it combines them in a way that it has not been done before, we have some hybrid bonding right now shipping, and we also have some SLC shipping with affordable cost. So this puts an outcap on the price, and yeah, I found it cool. The last thing I wanted to talk about is comprehensive evaluation. So they talk about the solution in every way possible, and yeah. Maybe some of the weaknesses. First, I would like to present to you this paper, which is an LPDDR-based CXL PNN platform for TCO-efficient inference on software-based large language models. The idea of this paper is to speed up server inference by using LPDDR5 enable memory. And as you can see, there is a lot of similarities between this stack of LPDDR5 and the one we have seen. So basically, they probably took this, they do mention this work quite a bit in the paper. So yeah. Also, this paper has implemented the solution in hardware. They have evaluated it using an FPGA, whereas Lincoln only uses simulations. So basically, similar ideas have been explored and implemented in a better way. Also, in the evaluation, there is a lack of accounting in context length. When you are running with very long context length, then the keys and the values you are storing in the DRAM become a huge bottleneck on the bandwidth. You have to read through them a lot, and since you have to go through every layers multiple times per second, it becomes prohibitively expensive. So they have not talked about this at all in the papers. And maybe since we have to load weights to NPU as well, it could be a problem if we have to load the DRAM, the keys and the values from the DRAM as well, since they are sharing some of the lanes. Also, the comparison to the base model does not make much sense, and some of the settings are not really well explained. What I mean by this is we are talking about running big LLMs. For the prefill phase, for one, they compare it to the base model, and they say, okay, the base model runs for 47 seconds before outputting a token. But this doesn't make any sense because you would never use this kind of model like this. Yeah. Then the last two things I have is Lincoln does not address software side. since it has to be controlled by the NPU, usually in modern computing, you would have a compartmentalization, meaning the NPU is running certain things and it doesn't have to know how the DRAM works. But the problem with Lincoln is since the NPU is controlling the DRAM, it will have to know how the DRAM works. And this means that if you cannot just plug it in and it works, you would have to reprogram the NPU, which is a separate device. Also, the LPDDR was not meant to be used with such high volume of data, and it may become clogged during LLM inference. So if we have the 100 gigabytes per second, which are used just to load weights for the LLM inference, then your device may become unusable during inference. All right, so now about the discussion. I have 3 questions for you today. So, I think it got into the wrong place. Yeah, okay. Okay, so, Yeah, it's fine. It just got into the wrong place. The slide got into the wrong place.
Okay.
It's fine.
Just move.
No, it's fine. I'm not sure what happened. Okay. So the first question is, how would you solve the drawback of the paper? So the first thing I'm thinking is with this LPDDR bandwidth clogging. Could you think of a way of solving this memory issue, this memory bandwidth issue, maybe?
I'm not sure, but maybe doing some computation in DRAM directly so that you don't have to, so that you reduce the data transfer over the LPDDR. So basically tackle it somehow so that you transfer less data over this interface.
Yes, okay. That's a good point. Then maybe, this is kind of, what would maybe some way of solving the difficulty of programming multiple components together?
Also gives this as a microphone.
Yeah, just maybe build some abstraction on top of all of these components that tie them together so that you better separate the concerns between the components.
Yeah, so this is kind of the same idea you said before. It's like you using the DRAM, like so using something in the DRAM to process the thing instead of sending them to the NPU, which is a different device. Yeah, so my idea is was using other lanes that may not be used. So for example, here there is Thunderbolt 5, which is coming and is providing way more bandwidth. So yes, Thunderbolt 5, it's not yet in computers, but it may provide significant boost. And yeah, I don't know what happened with the animations, but yeah, the thing is also bring the NPU closer to memory. So you can think this is the AI stick from Lenovo. So there is an IPU in it, and maybe, as you said, if we can put some the flash directly in the memory, then we can just program this as a black box from the outside. So the memory just has to travel between the flash and the NPU. Yes, okay, so then which other workloads could benefit from similar flash setup. So let's say you have Lincoln in your computer. What could other workloads that could benefit from this flash and enable DRAM be? Any ideas?
I think any workload that does like linear operations, because that's what we target, right? To do matrix or matrix vector multiplication. That would be one thing, and also any workload that's too large to fit into DRAM, so that it makes sense to move it to flash.
Yes, so exactly, we have so some workloads who have high memory footprints that cannot fit into DRAM, that needs high internal bandwidth, high read speeds, and high I/O bandwidth to the NPU or CPU. Also, yes, with the GMV operations, which are already directly integrated into the flash. Yeah. So, for example, I have other types of machine learning models. So we can think about convolutional models. Also, some graph things about nearest neighbor search, or database search of filtering, which usually this can be prohibitive. We have video transcode, and yeah, also like recommendation systems. Then maybe I just wanted to talk about. I think it's out of that. Yeah, so just a bit of background. This is a mixture of experts. The idea is to have a different, to only activate part of the feed-forward networks for each token. And so my point is, yeah, I think it was the one before. Yes. Yeah, so some architectures may actually not benefit as much. For example, mixtures of experts will not benefit as much from Lincoln. I think also about some bidirectional transformer models who could not really benefit because you have not the same caching. Yeah, also with the workloads we spoke about before, video transcode and that.
If you want to check.
Thanks. Video transcode and database search could not really use GMV acceleration. I can just. So my question is like, what other type of instructions could we implement near the memory? Does someone know what could be with some of these workloads? What could be implement? Yeah, and maybe to increase as well the part of the transform of the large language models that can be done in the memory. I mean, if no one has any idea, I can present my own. First of all, there would be some kind of general matrix multiplication that we could think about implementing with styling. And then the activation functions, it would be maybe a bit more complicated to implement directly on the device, but maybe we could do. And also quantization, some workloads require on the fly quantization, and if we do not have to move the weights to be able to quantize them on the fly, it may be also be beneficial. Okay, so going back to the next thing. Okay, so one of the problem is like some of the mathematical operations we talked about, so GMV or GEMM or even activation, differ a lot between them, and they may interfere. So the problem with Lincoln, it uses fixed hardware, and we cannot change what is done. So maybe if we're thinking about the future, maybe future LLM architectures may not be compatible with this Lincoln thing because it's too hard coded. And so my idea would be to use programmable accelerators to be able to reprogram on the fly with the things we need. So maybe the thing I had in mind was this smart SSD by Samsung, which utilizes Xilinx FPGA directly on the device, and this enables real-time. It enables to accelerate a lot of these video transcoding that cannot be done directly with GEMV. One thing to note is the internal bandwidth between the NAND flash and the FPGA is not very high. It's in a gigabyte per second, but not in the hundreds of gigabytes per second. And this means that if we want to be able to run large LLM inference, we still would need to use Lincoln Flash to be able to use these GEMV engines. Yeah. So this could also be used to calculate the self-attention and the activations of Lincoln. So it could totally replace the NPU in these architectures. Yeah. Also, some closing thoughts. We have talked about faster consumer device inference, but there is also a lot of research on faster server inference. And so here we have the Cerebras WSE2, and also we have talked about this paper a bit before. And the thing is, with this faster server inference, we can use bigger models like GPT-4o, which we probably never will be. Not in the near future, let's say, we will not be able to run on our device because even the number of parameters will take multiple terabytes. And also, when we run with these big models in servers, we have a speed of around 110 tokens per second, which is like 25 times the speed of what Lincoln could achieve, maybe. So even if we achieve to a real time LLM inference on consumer devices, people will probably still be using like faster server inference. Yes. All right, I think this is all I have. So if there are any questions, else.
Questions or comments from the audience?
Any comments?
I think this is an interesting paper because there have been other works that propose kind of in-storage processing using to accelerate LLM inference. So like this does something fundamentally different. It goes aggressively, first of all, into the storage system because it introduces a lot of modifications, shorter bit lines, multiple planes, more planes actually. It introduces new logic inside to perform the FP dot product, and it also this additional logic for the ECC. And it also does something different in another way. So other in-storage works try to perform extremely long context inference, and to achieve this, they store the model weights in the DRAM, and they store the KV cache in the storage. So this kind of takes an opposite approach to accelerate a slightly different workload, which in this case is mobile inference. So I think it has value, and it's a different approach compared to having more GPU power or processing power in general, which is the current trend. So yeah, I think it's interesting.
Yeah, this enables with only 32 tera operation per second, it enables a very large LLMs to be run. So yeah, it's still quite impressive.
Probably this is the way to go for mobile devices.
Yeah.
One more aspect that they don't look at is sparsity.
Yeah.
They also don't look at sparsity, I think, at this point, because a lot of data need not be brought over or used for computation. So
Of sparsity, yeah.
Yeah.
Indeed, like I spoke about mixtures of experts, but yeah, there are other type of optimizations that cannot be used with Lincoln. And this is also why I found it a bit strange to compare it, to compare Lincoln with with like a base model without any optimizations. There are a lot of the optimization, like low rank approximation, sparsity induced weight loading, and yeah, mixture of experts that could really speed up the base thing, yeah, the base model.
I'll make a comment too. Is that your microphone?
Yes.
Okay. Hey, thanks for the presentation. I agree that this is definitely an interesting paper, and it's good to look at these emerging technologies like 3D stacking, especially when they enable multiple different types of memories to be put together with logic. I agree that I think maybe it's a bit early because a lot of optimizations are not incorporated yet, like sparsity, and the models are also evolving, right? It's not clear if this is the model that will be used, but it's good to explore technology and application together, in my opinion. So maybe over time, things will become more flexible and you can actually exploit different types of workloads on top of the substrate. So I like the combination of DRAM and flash, and as technology integration becomes better and better, you can put more and more also, right? More DRAM, more flash, more compute. But in the end, you're limited by thermals.
Go ahead. So we were discussing with what actors participate in the group. What is the limit? How much logic can we get away with putting in the storage system to accelerate such kinds of workloads? And that may be something that we want to look into. So yeah, that's what I had here.
I guess that's it for this part. Let's take a break for 10 minutes and be back with a separate presentation.
And then we can just
Yeah, that's fine.
I just wanted to check why this thing doesn't work.
close this. It's stuck.
Here, there are tabs. Yeah.
So this works. Okay. Is it moving? Okay.
I'll check YouTube.
And then can you hear me talk? Can you maybe or maybe you should talk and I will listen. So talk that.
Yes.
I can hear you. Can you use the other one?
We need to turn it on.
It's on.
Test. Test.
But is it this one or am I listening to the one?
Should I go?
Yeah.
Maybe it doesn't have a lot of buzz.
Because I understand this is the battery it's full,
Yes.
but this thing is really cheap and so I'm checking the mute, but I can only find one mute button here. Unless this is.
Maybe we could just use mobile.
Yeah.
Then I log in.
Thank you, guys.
Six like that. Okay. on Zoom? Thank you.
You can start. Okay, let's start. Are you ready?
Is it on or not?
Can you speak
Hello? Test.
again?
Test.
Okay. Yeah, you can just make it yourself a clip. Yeah, can you introduce you?
Welcome back to the seminar. So next presenter is Alec Gersberger. He's a sixth semester bachelor student in computer science, and his interests lie in computer architecture and high performance computing. So he's going to talk about an interesting work on in-flash processing in NAND flash memory using the inherent capabilities of the substrate. And I hope you find the talk interesting. Thank you.
Thank you. So welcome from me too. So I'm going to present you Aries Flash, efficient parallel integer arithmetic operation using NAND flash memory. So first, an executive summary. So the problem we are facing is the data movement between compute units and the memory hierarchy significantly affects the performance and the energy efficiency of the computations. And we can solve this problem by doing in-flash processing. So, and there are two ways to achieve in-flash processing. The first ones are the idea is to add additional circuit components to support complex operations, which then, however, results in higher area overhead and also increased energy consumption of the device. And the second approach, which we are going to focus today on, is the in-flash processing works without expensive hardware modifications. However, they are constrained to bitwise operations only. So the goal of Aries Flash is to perform arithmetic operations like addition and multiplication, utilizing the operation principles of NAND flash storage. And they leverage a page buffer design with controls to perform arithmetic operations, and also propose a transmission circuit to enable transfer-free bit shifts without using the internal channel. And they evaluated Aries Flash on 3 real-world workloads by simulating the performance with MQSim, and achieved up to 18.5x and 9.9x performance improvements over out-of-storage processing and in-storage processing, and also 97.9x and 14x more energy efficient than out-of-storage and in-storage processing. And the mechanism that they use uses 0.84% area overhead compared to commercial 3D NAND chips. So first, I'm going to give you a little background on the structure of flash memory, and then I'm going to walk you through the Aries Flash implementation, then be taking a look at the evaluation, and to wrap it up, I'll tell you about the strengths and weaknesses of the paper that I've identified, and at the end we will discuss the paper together. So for the background, and first here you see a broken down, simplified architecture of traditional outside storage processing systems, where we have the data in the storage read it to the main memory, read it to the host processor, and there happens a computation. So as we all know it, and then we write it back. And here, obviously, it's the data movement bottleneck between the main memory and the storage, because we only have around 8 gigabytes per second bandwidth compared to hundreds of gigabytes per second from main memory. So this is where near data processing comes in. There are multiple approaches like in-cache computing, processing in memory, in storage processing, and in flash processing. And we are going to focus today on those two because we want to solve the problem of large data sets that do not fit into main memory. So now let's take a look on how a NAND flash SSD is built. So here you see the broad architecture of a SSD, where you have the SSD controller, which is responsible to communicate with the host. It also performs error correction, garbage collection, and also address mapping. And it is connected through multiple channels with multiple flash chips. Each of these flash chips contain multiple concurrently operating dies, and each of those dies contain multiple concurrently operating planes. So we have massive levels of parallelism that we can leverage, namely chip, channel, die, and plane level parallelism. So then inside of these planes, we have a page buffer and many storage blocks. So the blocks are the units where we actually store the data, and the page buffer is used to read and write data to and from the blocks. So, and for the blocks, which are here, they consist of vertically and horizontally stacked cells, where the vertically stacked cells are connected through a bit line, and the horizontally stacked cells are connected through the word line. And we read and write data on for one word line at a time. So, yes. So then the flash cell itself, it's basically a transistor which can hold electrons in a non-volatile manner. And this then changes the cell's threshold voltage. So if we have some reference voltage and we apply it to a first cell with a low charge level, it behaves like a resistor. So the current can flow through the cell. And if we have a programmed cell with a high charge level, the reference voltage is not high enough, is below the threshold voltage of the cell. So the cell operates as an open switch. Then for the page buffer, it consists of multiple latches for each bit line, and this is and we read and write data to and from the blocks from here. So we have multiple latches, and for each bit line we have these multiple latches. So now let's look how we read actually data. So here you see the latch circuit that Aries Flash proposes, where you have a capacitor here, we have the sense outline, and down at the bottom it's connected to the bit line. So first we open M3 to set the sense outline on high, which then charges the capacitor C. Afterwards, we open the transistor M2, which resets the latch such that we have a 1 stored in it. And then we again close M2, close M3, and we connect the capacitor C to the bit line. And now if we have a cell, we read a cell with a stored value of 0, it behaves as an open switch. So C does not drain, and thus the ML transistor is activated because SO is on high. If we then activate M3, we will ground A, so it's pulled to ground, and we have the value 0 inside of the latch. Then if we read a 1, the cell behaves like a resistor, and C drains through the bit line. So ML is not activated, and if we open M3, nothing happens, and we have still a 1 inside of the latch. So if you remember from the talk before, here you see the single level cell voltages that are possible. So we have two types of voltages where we have the low threshold voltages for the earth cells and the high voltages for the programmed cells. And you can see that's a distribution because in the real world, nothing is perfect. And if we now apply the reference voltage somewhere between those two lumps, we can, in theory, read out the correct data. However, in practice, the distribution looks more like this, where we have some overlap. And this is due to that NAND flash is highly error prone. And so for reliability, we need error correction and data randomization. However, for error correction, we have to move all the data to the SSD controller first because the SSD controller is the one responsible for error correction. So Aries Flash applies a technique that is proposed by Flash Cosmos, which is a prior work, where the idea is to improve the reliability by widening the margin between the two states, between the two voltage levels. However, you sacrifice programming latency for reading accuracy. So now that we know how an SSD looks like, I can introduce you to in-storage processing, where the idea is to have an in-storage computation unit where you read the data to it from the NAND chips, then do the computation there and send the results to main memory and then to the host. And yes. However, we just moved the bottleneck from outside the storage inside the storage. And in flash processing, in contrary, performs the computation entirely inside of the NAND chips. So we only send back the results to the in-storage computation unit, which then does maybe some more processing and then sends it back up the memory hierarchy. So how do we do that? Parabit performs bulk bitwise operation by controlling the latch circuit of the page buffer, where here you have a NAND flash chip where we have some operands stored, and we then read each of those operands into the page buffer sequentially and then do the computation inside the page buffer. So read A, B, and C, and then accumulate the result in the page buffer. However, here, the serial data sensing is the bottleneck in this processing technique, and we can do better. Namely, Flash Cosmos improves this by simultaneously sensing the operands. And if you do this clever enough, you will only have to do one read and get the result directly in the page buffer. However, this is still limited to bitwise operations. So we have seen that it is possible to do bitwise operations in flash memory with minimal hardware modifications. However, to perform complex operations, for example, for addition, we have to move the carriers through the flash controller, which results in data movement and thus high latency. So the goal of RS Flash is to perform the arithmetic operations by utilizing the operation principles of NAND flash storage. So how do we do this? The idea of Aries Flash is to use the page buffer to perform the computations. And if you activate transistors in a certain sequence, you can execute these operations. So this is the computing platform of Aries Flash. And now let's take a look on how they implemented the AND operation. So now let's assume we have read A equal to 1 into the first latch, then B equal to 0 in the second latch, and we initialize C to be 0, where we then will have the result, and we also have pre-charged the capacitor. So we first turn on M1, and since the not A line is 0, sends out is not pulled to ground, and we then turn also M5 on. However, since not B is in high voltage, the sense out line will drain to ground. And now we can just read the sense out value into C by activating M10. However, since sense out is not high, nothing happens, and we stay at 0. We can also do this in place, where we now have, where we essentially override one operand to have the result stored in there. So now we have A equal to 1 and B also equal to 1, and we also have pre-charged the capacitor again. So if we turn on M8, the sense out line will drain through the latch, and then we can turn on M3. However, since B is already equal to 1, the result is equal to A. So yeah. We can also do it for OR, where the idea is essentially the same. However, we only we turn on some other transistors, and yes. So with these operations, we can implement a 1-bit full adder by having where we have we first load X into first latch, Y into the second one, and then we AND them together. We afterwards XOR them together, and afterwards we have to load the carry in from the previous digit into the first latch again, and then we can finish the calculation by sequentially doing these operations here, and then we will get the result in the latch 2 and the carry out in the fourth latch. So a 1-bit full adder, we can implement additions for high bit widths. So where we store the operands horizontally in the word lines, and then read both operands into the page buffer, and then we can execute step 1 and 2 simultaneously for all the digits. However, since we have the data dependency on the carry in, we have to sequentially let the carry in propagate through all the digits, and we have quite low utilization. And in the end, we can finish the calculation again simultaneously and then output the result. We can also change the data layout, and by storing the operands across word lines such that they share the same bit line, and then we just repeat n 1-bit full adders if we want to add two n-bit numbers together. This eliminates the idle time for the carry-in propagation. However, it sacrifices plane level parallelism, and for accumulation you have to use intra-die transfer. So I've talked about transmitting 1 bit from one latch circuit to the next. This is done using a transmission circuit, which they propose, because using the internal bus to transfer the carry-ins, this increases the operational latency. So they propose this circuit to be able to send the carry out from the lower digit to the higher digit from the fourth latch into the first latch, and yes, by just enabling the bottom line. They also have to be able to control this the transmission circuit to support flexible bit widths, and they do this by cutting off the connection between adjacent data, because otherwise you will send the carry out from one addition, for example, to independent data, which we don't want, and their implementation has up to 32-bit support. Then for multiplication, this is where it gets funky. So we store the operand A in the latches, and the operand B we move to the flash controller. So we have some data movement, and we have to send half of the data to the flash controller, which isn't that great, as we'll see later. And then, depending on the value of the ith bit of B, we send different commands. Namely, if we have a 0, we just shift the operand that is stored in the latches, and if we have a 1, we first add the previously shifted operand to a intermediate result, and then shift it. And we do this for every digit of B. So, and since all chips share the same flash controller, we have to send the flash commands for different chips interleaved. And so we can also have only one multiplier for a single plane at the time. So all this hardware generates some area overhead, where we have 5 latches per bit line and 2 extra transistors per latch. And the transmission circuit requires 2 additional transistors per bit line. And this results in 0.84 area for percent area overhead compared to commercial 3D NAND chips. So now for the evaluation, they compared it to 2 baselines, namely for outside storage processing, they used a CPU for the computations, and they measured the energy consumption with Intel grapple. For the in-storage processing, they used an FPGA for the computations, and they measured the energy consumption directly from the FPGA board. And for air as well, it performs operations inside the NAND chips, and they simulated the performance using MQSIM, and they estimated the power draw based on the maximum power of a Samsung 990 Pro SSD. So first they benchmarked the accumulation operations by having some k-means clustering workload. In this graph, you see the normalized to out-of-storage processing throughput for different sizes of dataset segments. And yes, so here we see that RSH, which is the dark blue one, has large performance gains with smaller data widths. So with 42-bit integers, it loses against RSV. However, for 4-bit integers, it quite significantly outperforms RSV. And RSV is relatively constant in terms of performance gains, independent of the data width. So then here you see the numbers. Yeah. So they also tested page rank, where we again have the same normalized throughput for increasing dataset sizes. And here we additionally see that RSH again has better performance with smaller bit widths, and also that it has large performance gains with larger data size. And RSV again is just constant. And here we have roughly the same numbers again. Now for the multiplication, they used vector-vector multiplication, and again, the normalized to out-of-storage throughput. So RSH matches the performance of in-storage processing for 16-bit integers, and for 4-bit integers, it's quite good. And again, it gets better with smaller data width and larger data size. However, RSV only barely outperforms in-storage processing under Int4, and it only gets worse as you increase the bit width. And I think they didn't even bother to show 32-bit integers. So yeah. Now for the energy efficiency, here you see the normalized to out-of-storage processing bit per energy. We have quite good energy savings with almost 100x improvements over out-of-storage processing, which is great. And these improvements are due to the reduced end-to-end latency and lower device power requirements of Iris Flash. And for the vector-vector multiplication, we see for RSH, again, a similar picture. However, for RSV, we have well, it's worse because also the performance is worse, so it just makes sense. So in conclusion, we have seen that Parabit and Flash Cosmos only provide limited computation support, and that Iris Flash leverages a modified page buffer design to and transmission circuit to implement full adder logic and bit shift mechanisms. And they tested on real-world workloads that Iris Flash outperforms traditional out and in storage processing in accumulation and vector-vector multiplication tasks. So yeah, now for the strengths. So first, they successfully reduced the data movement, which results in improved energy efficiency, and also they achieved good performance by utilizing the parallel nature of NAND flash, and they also did this with minimal hardware modifications. And for the weaknesses, the multiplication, as we have seen, has quite a bit of overhead, where we have to move half the data to the flash controller, so this is not great. Also, they did not provide a comparison of the bitwise operations performance with Parabit and Flash Cosmos, and they were specifically only designed for these bitwise operations, which I think would be quite interesting. And this is more a point for all in-flash processing techniques, that Ars Flash is not designed to be used with a standard encryption method. So we need fully homomorphic encryption. However, there will, I think there's, it's an active research area, so there will be something later. And also in the paper, they have errors in figures, and also have like a plot where they show 20 times the same bars, which I think is a bit unnecessary, or they didn't even mention it in their text. So I was wondering why that would be so. And they also provided some wrong transistors in the implementation of the logic operations itself. So do you have any questions? Doesn't seem so. So let's discuss. So how might we improve the performance of Iris Flash? Do you have any ideas? For example, the multiplication would be a start, or just the logic implementation. All right. So for the multiplication, we could add hardware closer to the bit buffer itself. So we would have less data movement, or just have to move the data within the flash chip itself. And yes. And for the logic operations, we could only read one operand into the latches, and then get the right state of the sense outline by directly reading the data from the flash cells. So, and we could also add Flash Cosmos functionality to process multiple operands simultaneously. But so how might we extend Iris Flash to support more complex operations? So maybe floating point support, or matrix multiplication, or something. So for floating point support, this just requires additional multiplication and left-jits, which we have. So for multiplication, we can just store the mantissa and the exponents in different planes, and then sum up the exponents and multiply the mantissas together. And however, we should we would have to check for if we have to do rounding. And for addition, we would also have to have the ability to dynamically shift the mantissas. So, and for matrix multiplications, I thought where we just store the one matrix across the planes and the other one near the flash controller, and we just can leverage the high parallelism that matrix multiplication that Aries Flash provides. And can we extend Aries Flash to support denser technologies like triple level cell or quad level cell, where we just have more bits per cell?
So I guess we would need even stronger error correction than that.
Yeah.
Yeah. And so right now we don't have any error correction in this solution, right?
Mm-hmm. Yeah.
So we would have to move the error correction into. It would be have to be done internally, not externally by the controller, right?
Yeah, exactly. Yeah. Yeah, that's what I thought. And also we would have add more latches to the page buffer, and then we could split the page buffer such that we can operate on each bit of the multi-level cell concurrently. And as here, move the error correction closer to the planes, or have something like the ESP, it's wrong, for multi-level cells. So, and yes, this is the wrong question, but we can also discuss it. So how might we integrate in flash processing and processing in memory, for example, to create a synergistic computing system that maximize performance, energy efficiency, and data movement reduction? So, yeah.
Maybe you can do some offline profiling before on the benchmark or on the workload you are going to run, and then decide offline what computations you are going to offload to BIM and which ones to the in-flash processing. That would be a way. Maybe also if you don't want to, if you cannot do offline profiling, maybe you can take some decisions online, maybe implementing some, I don't know, machine learning based decisions such as reinforcement learning or such.
Yeah. So I thought you can just, you would have to do some offline benchmarking on whether on what, so to just bring the data size down in flash and then send it to processing in memory stuff, or just the host. And then you have to find the right trade-off between performance and data movement overhead or reduction. So yeah, and yes, it would enable fine-grained control over performance versus efficiency. So we could optimize for one or the other. So that's it. Thank you for your attention. And do you have, again, other questions?
So thanks, Alec. I'll make a final comment on this. So this is kind of a very active area of research, because, as you know, storage is kind of the place where you can store large data sets, and processing in storage is perhaps the last mile in kind of near data processing. So if you look at this work, there is still a lot of potential to improve it, because you still have to move a lot of data to the latches and then perform computation there. Flash Cosmos tried to improve it by performing more computation, with a single sensing operation, but there is a lot of, again, we are still only scratching the surface in terms of what we can do here. We can look at different kind of applications like LLM, acceleration, graph processing, and many such active applications which can be benefited by performing computation closer to where the data resides. So if anyone is interested, we can discuss more, we can collaborate, and please let us know. And yeah, that's my comment. So thanks, Alec. for the presentation. And I think if there's no more comments, then we can close it. Thank you.
Thank you.